Rahim. Assalamu alaikum dear students. This is our next problem. Problem having been once again chosen from the book Modern Physics by Kenneth S. Crane. As usual, we first come to its statement. Okay. A collection of hydrogen atoms is placed in a magnetic field of 3.50 Tesla. Ignoring the effects of electron spin, find the wavelengths of the three normal Zeeman components of the 3D to 2p transition. Okay. A collection of hydrogen atoms is placed in a magnetic field of 3.50 Tesla. Ignoring the effects of electron spin, find the wavelengths of the three normal Zeeman components of the 3D to 2p transition. Transition is from 3D to 2p. Dear students, this problem is not so simple, and our methodology is that in order to meet harder problems, we make use of helping tools relatively more. Okay, so that when we go through those helping tools, we develop some foundation for understanding this problem, that problem accordingly. Okay. Otherwise, without these helping tools, our length of problem will be reduced, but for the viewer, for the listener, for the beneficial, this thing will not be appropriate. Okay. So as usual, we first come to helping tools. Okay, helping tools. Tool number one. Tool number one is regarding energy levels of hydrogen. En is equal to minus so and so, and this is alternatively equal to minus 13.60 electron volt over n square. Okay. Dear students, here we will not apply this intermediate portion. Okay, we are concerned only with this value. Okay, minus 13.60 electron volt over n square. Okay, n is equal to 1, 2, 3. Energy levels of hydrogen, En equal to minus 13.60 electron volt over n square. Dear students, in the next version of this helping tool, the same philosophy has been repeated in a slightly different mode, in a slightly different pattern. Okay. The principal quantum number n determines the energy levels in hydrogen. En equal to minus so and so, and this is equivalently equal to E1 over n square, and this is equivalent to minus 13.6 electron volt over n square. Okay, for n equal to 1, the electron is most likely to be found 1 Bohr radius A naught from the nucleus. In higher energy states, it is likely to be farther away. Okay, when n is equal to 1, electron is most probably occasioned in Bohr radius, which is denoted by A naught, and its value will also be given in some other tool hereinafter. Okay, now we move to tool number 2. Okay, dear students, this tool has been used so many times in our previous problems that I think we should not discuss this tool in detail. Okay, momentum of a photon E is equal to E over C equal to HF over C is equal to H over lambda. Okay, so we skip this tool because this tool has been utilized several times in our previous problems. Next, tool number 3. This is also a table, and this table has also been used so many times in our previous problems, so we do not need to discuss it in detail. Okay, so we also skip detail of this tool. Okay, next, tool number 4. Yes, this tool is appearing first time in our problems in our videos. Okay, this is new tool. This tool is being used or utilized first time in our problems, in our videos. Normal Zeeman effect or Zeeman effect, whatever may be the exact pronunciation. Okay, pronunciation is always our second priority. Okay, normal Zeeman effect is equal to delta lambda is equal to lambda square over HC delta E. We know that delta denotes change. Okay, delta E denotes E2 minus E1, delta lambda denotes lambda 2 minus lambda 1. Okay, etc. This alternatively becomes equal to lambda square over HC into mu B, where B is written as a subscript of mu, and then it is multiplied with B. Here B is magnetic field and mu subscript B is Bohr Magneton. We will define this term in another helping tool which will come hereinafter. Okay, next tool number 5. According to tool number 5, 1 Tesla, which is denoted by 1 T, is equal to 1 Newton over ampere meter. Okay, in tool number 5, Tesla is defined. Okay, unit Tesla is defined. Then its second version is given, in which 1 Tesla equal to 1 T is equal to 1 Newton over Coulomb into meter over second. Recalling that a Coulomb per second is an ampere, we have 1 Tesla equal to 1 Newton over Coulomb over second into meter is equal to 1 Newton over ampere meter. An earlier non-SI unit for B still in common use is the Gauss, capital G, and 1 Tesla is equal to 10 raised to the power 4 Gauss. 10 raised to the power 4 means 10,000. Okay, one Tesla is equal to 10,000 Gauss. This is just a conversion factor. In this problem, I think it will be not in our primary use. However, in order to develop a foundation for understanding this problem, this conversion factor is necessary. Okay, dear students, in tool number 6, Bohr magneton is defined. Bohr magneton mu b. Here b is written as a subscript of mu. Okay, mu Bohr magneton mu b, where b is written as a subscript of mu, is equal to E h cut over 2m. We know that h cut is equal to h over 2 pi. H is Planck's constant, and h cut or h bar or h reduced is Planck's constant h divided by 2 pi, where pi has a value 22/7, which is taken equivalent to 3.14, and decimal representation of pi is non-terminating and non-repeating. It goes endlessly. Okay, Bohr magneton mu b is equal to Bohr magneton mu b is equal to E h cut over 2m is equal to 9.274 into 10 to power minus 24 joule per Tesla is equal to 5.788 into 10 to power minus 5 electron volt over Tesla. So these two expressions are equivalent. Okay, one is in terms of joule and the other is in terms of electron volt. Okay, while Tesla is in both. Okay, dear students, next tool, that is tool number 7, is about magnetic field B. Okay, magnetic field B. A magnetic field B is defined in terms of force FB, where B is written as a subscript of F, acting on a test particle with charge Q moving through the field with velocity v. Fb is equal to Qv into B. The SI unit of B is the Tesla, T, capital T. 1 Tesla is equal to 1 Newton over ampere meter is equal to 10,000 Gauss. Okay, 10 to power 4 means 10,000. 10 to power 3 means 1000. 10 to power 2 means 100. And 10 to power 1 means 10. Okay. Now we move to solution. Dear students, in solution we will just apply tools which we have discussed above. Okay, using above tools our problem will be automatically solved. Okay, just we will have to find we will have to put the values and then simplify the expression. Okay, now using En equal to minus 13.6 electron volt over n square, we have delta E equal to E3 minus E2, because dear students, we are dealing with the transition from 3D to 2P, 3 to 2. Okay, Yes, dear students, Adhan has come to an end, and now we start our problem from the same point where we left. Okay, using En equal to minus 13.6 electron volt over n square, we have delta E equal to E3 minus E2, because we are dealing with the transition from 3D to 2P, 3 to 2. Okay, so delta E will be equal to E3 minus E2, and in this expression, once we will put n equal to 3, and then we will put n equal to 2, and then we will subtract these. Okay, when we will subtract E3 minus E2, and E2 is already negative, so it will become positive. Okay, because we know that multiplication of two similar signs always gives positive result, while multiplication of two different signs gives negative result. Okay, so here E3 will become minus, but because E2 is already minus, so when minus is multiplied twice, then its result will be positive plus. Okay, so this is the value of E3 and this is the value of E2, and moreover in the next step we have just simplified these two. Okay, it becomes minus 1.511 electron volt, and it becomes equal to plus 3.4 electron volt. Okay, here dear students, because plus figure is greater, so our result will also be in plus, and hence delta E becomes equal to 1.889 electron volt. Okay, I think to this extent there should be no confusion. Okay, now lambda is equal to Hc over E. This is also a tool which we skipped, because we have used this tool so many times that wasting time on this tool again and again is inappropriate. Okay, so this expression is taken from our helping tool. Moreover, the combined value of Planck's constant H and C is also given in another tool in which a table is shown, and we skipped detailed discussion of this tool, because this tool has been used several times earlier in our previous problem. Okay, so in this tool, in this table, combined value of Hc is given as 1240 electron volt nanometer, while we have already calculated value of E. Okay, 1.889 eV. Yes, students, we are seeing that here we have used delta E, but here we have used simply E. So I think it should be understood. Okay, in formula there is only E, not delta E, but the value, actual value will be of delta E, because in our statement we have been given two energy levels. Okay, 3D and 2P. Okay, so their net effect will be taken here. Moreover, in the tool in which a table is given, in which separate values of Planck's constant and H and speed of light C are given, and then their combined value is also given. Okay, so it is our discretion whether we separately multiply these two factors or we take jointly calculated value of this pair. Okay, so we have availed this facility that we have not used separate values of Planck's constant h and speed of light c, and we have chosen combined value of these two factors. Okay, so after simplifying, it will become wavelength lambda equal to 656.43 nanometer. Okay, next, dear students, we are going to Bohr Magneton. We have in our previous steps we had reserved one helping tool for Bohr Magneton. Okay, in one helping tool we had just defined the term Bohr Magneton, denoted by mu b, where b is written as a subscript of mu, where b is magnetic field. But here it gives rise to a new term, Bohr Magneton. Okay, we know that Bohr Magneton mu b is given as mu b is equal to 9.274 into 10 to power minus 24 ampere meter square, and is alternatively equal to 9.274 into 10 to the minus joule per Tesla. Okay, dear students, when we defined this term in our helping tool, we had expressed this value in two equivalent expressions. Okay, so these are two equivalent expressions. It is our discretion whether we use this or we use this. Okay, both are equivalent. Moreover, we know that normal Zeeman or Zeeman effect is given as delta lambda equal to lambda square over hc into Bohr Magneton mu b, where b is written as a subscript of mu, into dot meaning a sign of multiplication. Okay, multiplied by b, that is magnetic field. Okay, this alternatively becomes equal to what we have done here. We have just used the value of lambda which we have calculated in our previous step. Okay, this is lambda square and this is hc, this is h, Planck's constant, and this is c. Okay, dear students, here once again we had an option to whether we use combined value of this or we use separate values of h and c. Okay, so here we have exercised discretion that we have not taken combined value of Planck's constant h and speed of light c. Okay, rather we have taken separate values of these two constants. Okay, h is separate and c is separate, multiplied with, in place of Bohr Magneton we have used this value which was in terms of joule per Tesla. Okay, we revert to our previous step. Okay, here. Okay, dear students, Bohr Magneton has been expressed in two equivalent expressions, in two equivalent forms. One is in terms of ampere meter square and the other is in terms of joule per Tesla. We have used this second alternate expression. Okay, we have omitted this first alternate expression. Okay, so what we have done, in place of Bohr Magneton we have used this value which is not in terms of ampere meter, rather it is in terms of joule per Tesla, multiplied with B, magnetic field. This is given in the statement 3.50 Tesla. Okay, Next, in the next step, we will just simplify it. Here, dear students, you can see that Tesla will be cancelled with Tesla. Okay. Moreover, yes, Joule will be cancelled with Joule. Second will be cancelled with the second. So let us see what happens in next step. Next step becomes equal to this nanometer square. Actually, square of this is equal to this, and square of nanometer is nanometer square into here, dear student, Tesla will be cancelled with Tesla, and when this will be multiplied with this, we will get this. Okay, and in the denominator we have simplified. How simplified? This 3 has been multiplied with this 6.626, and it has taken the form 19.878. Okay, so nothing, no rocket science, just simplification mathematics of about primary or secondary level. Okay, so dear students, here this 10 raised to the minus 26, when shifted to a numerator, it will become plus, and this plus will dominate, and this 24 will be subtracted from this 26, and we will be left with 10 raised to the power 2 in the numerator. Okay. Moreover, dear students, nanometer means, we know that nanometer means 10 to power minus 9 meter, and nanometer square will become equal to 10 to power minus 18 meter. Okay, I think it should be quite clear. Such minute things need not to be explained. Nano means 10 to power minus 9. Nanometer means 10 to power minus 9 meter. And nanometer square means 10 to power minus 18 meter. So, in place of nanometer square, we have used 10 to power minus 18 meter. Okay. Yes. Okay. So, dear students, in the next step, this is just simplification. Just simplification gives rise to this form. Okay, 703621799.998 into 10 to power minus 18 meter, and dear students, this figure can be written as 7.03 into 1, 2, 3, 4, 5, 6, 7. Okay, 7.0 into 10 raised to the power 7. Okay, 10 raised to the power 7, that is plus. It is 10 raised to the minus 18 minus. So their net result, rather we have written it in this form, 0.07. Then it will be written as 10 to power plus 9. It will be written 10 to power plus 9, and this is 10 to power minus 18. So net result will be 10 to power minus 9. Okay, and we know that 10 to power minus 9 is nano, and hence result of this simplification becomes equal to 0.07 nanometer. 0.07 nanometer, because 10 to power minus 9 is equal to small n nano. Now, in presence of lambda equal to this nanometer and delta lambda equal to this nanometer, we have, because we have to find out 3 values. One value is this, and other two values will be of this nature that once we will add this value in this value, and in the second time we will subtract this value from this value. Okay, in this way we will get three values. Okay, now in presence of lambda equal to this so nanometer and delta lambda equal to so nanometer, we have lambda 1 is equal to lambda plus delta lambda, and this becomes equal to 656.50 nanometer, and in the second place we will subtract delta lambda. Okay, actually this factor, that is delta lambda, which has become equal to 0.07 nanometer, is going to be added one time and subtracted one time from main value of lambda, and in this way we will get three values. Okay, one value we have calculated already, and remaining two values will be calculated in this way, that once we will add this value to that first value, and second time we will subtract this value from the first value, and hence in this way our three values will be completed. Okay, now in presence of lambda equal to this and delta lambda equal to this, we have delta 1 is equal to this plus this, and this becomes equal to this, and delta 2 is equal to delta lambda minus delta lambda, and this becomes equal to this. Okay, we see that both are nearly equal, but because plus minus operation has been applied, so some difference exists, and hence we have find all the three values. Okay, which three values? One value is this, other value is this, and other value is this. Okay, three value, we have to find out three values. One value is 656.43 nanometer, second value is 656.50 nanometer, and third value is 656.36 nanometer. Okay, so these three values are our answer, and this is the end of our problem. Till next video, Allah Hafiz.